Good afternoon, guys. Myself, Sridhar H, working as the assistant professor in the Department of Electronics and Communication Engineering at Government Engineering College, Haveri. Today, in the session 6, we people are just going with the decoder and mux of Module 5 Digital Electronics Fundamentals of the subject Basic Electronics. That subject code is 18ELN14 or 2 4. Okay, so in this session, in the previous sessions, we are just going for this adders. So this one is the continuous form of this adders. Okay, it's applications of adders. In adders, what we people have studied is half adder, full adder using two half adders, as well as ripple bit carry, that is 4-bit ripple carry adder. Okay, next, first thing, decoders. What is this? Decoders are the other important type of combinational circuits. Okay, next, among other things, they are useful in selecting a memory location according to binary value placed on address lines of the memory bus. Okay, so this one is just for the memory locations what way people are been using this decoders. Address decoders with n inputs can select any of the 2 raised to n locations here. So if I just go through the block diagrams, it is having n number of inputs and 2 raised to n outputs. So that is, so we can just mention it as 2:4 decoder, or 3:8 decoder, or 4:16 decoder. Okay, that is 2 square is the thing. Okay, next, address decoders with inputs and can select 2 locations. The outputs of the decoders are nothing but the minimum terms of an input variable signs when it is enabled. Okay, so 2 to 4 decoder. Next, 2 to 4 decoder has 2 inputs. Two inputs are the what? A1 and A0, and 4 outputs, Y3, Y2, Y1, Y0, and another one is the thing enable. Okay, so this one is enable, just acting as a switch to make the decoder on or off. Okay, and it is totally depend upon the designer. So when he has been placed, so whether if A is equal to 0, your decoder will be working, or if E is equal to 1. Normally what it will be having is, when enable is equal to 1 only, the decoder will be just acting as a on state. One of these 4 outputs will be on, one of the with enable E is equal to 1. So this one is the one what will you just consider. One of the means another thing. So only in this, so though there are 2 inputs and 4 outputs, only will be considering for the one output. Okay, so this one is just the truth table of your 2:4 decoder. See here, when enable is equal to 0. Okay, see here, if enable is line, so 2 inputs A1 and A0, and the 4 outputs Y3, Y2, Y1 and Y0. When enable is equal to 0, whatever might be the inputs, the outputs will be always 0, because enable you take considering it as 1. When enable is equal to 1, see next the 4 combinations 0, 0, 0, 1, 1, 0 and 1, 1. What will happen when enable is equal to 1? When the inputs A1 and A0 both are 0, only my Y0 will be high, remaining all bits will be 0. When that is here, when A1 and A1 is 0 and A0 is 0, only Y0 is 1. When it is 0, 1, so Y1 is 1. When it is 1, 0, Y2 is 1. And when it is 1, 1, Y3 is 1. See here, whenever people are been representing the decoder, see here, it should be in a diagonal position. See here, for 0, 0 it is Y0, for 0 it is Y1, for 1, 0 it is Y2, and for 1, 1 it is Y3. Always it should be mentioned in a diagonal position. Okay, next, what is the expression what I will be getting? It is the expressions here for Y0. Oh, sorry, first we will go through the Y3 or Y0, whatever, whichever you feel is the Y3. For Y3 it is what we will be having, enable is equal to 1, A1 is 1, A0 is 1. So what our expression is E A1 A0. See here, E A1 A0. Okay, the expressions here for Y3 it is only 1, that is E A1 and A0. For Y2 it is what? E A1 and A0 dash. See Y2 E A1 and A0 dash. For Y1 it is what? E A1 dash A naught, E A1 dash A naught, and for 1 it is what, E A1 dash A naught. Okay, so only thing what you should be remembering in this one is what, so the decoder, it should be in a diagonal position. See next, so this one is the logical diagram. Depending upon these expressions, we have just drawn the schematic diagram. A1 8 and the thing, Y3 is what, enable Y1 A1 and A naught. For Y2 it is what, enable is 1, it should be next A1 A naught bar. Next for Y1 it is, means whatever the connections will be having, so depend upon that. Enable is 1, next A naught and A1 bar. And for it is, for Y0 it is what, enable 1 A0 bar A1 bar, or A0 dash and A0 dash. So this expression they are just drawn by using this expression, that is the logical expression what we people have got from this truth table. Okay, next in the same fashion, if I want to design for 3:8 decoder, what it will be having, it will be having 3 inputs A, B, C, that is 2:0, 2:1 and 2:z, and the enable line. Okay, see this one is a simple thing. So in this truth table they have not mentioned the enable line, so it is just the A2 A1 A0. So it is having 3 inputs, means 8 combinations it will be having, 0 to 7, 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 and 1 1 0 and 1 1 1. Okay, see, and the 7 that is 8 outputs, D0 to D7, D7, D6, D5, D4, D3, D2 and D0. So 1 it is 0 0 0 what, D0 is 1, for 0 0 1 it is D1, for 2 it is D2, for 3 it is D3, for 4 it is D4, for 5 it is D5, for 6 it is D6, and for 7 it is D7. So yeah, once again if you want you can just check it, what the ones whatever in a decoder is what, it is diagonal shape. Okay, for 0 it is D0, for 1 it is D1, for 2 it is D2, for 3 it is D3, for 4 it is D4, for 5 D5, D6 it is 6, for and the last is D7. Okay, next, now the expression what I will be getting is here, what, for D0 it will be what, A bar, A2 bar, A1 bar, A0 bar, or A2 dash, A1 dash, A0 dash. Okay, and for 1 it will be what, for D7 it is A2, A1, A0. Okay, next, the applications of decoder. The decoders were used in analog to digital converters, in analog decoders, and it is used in electronic circuits to convert instruction into CPU control signals. The mainly used in logical circuits are for data transfers. Next, so after decoder it is multiplexer, and in simple it is known as the MUX, and it is also a combinational circuit, and it is designed to switch on of the several input lines through to a single common output line by the application of control signal. Okay, in the decoder it was having what, so many inputs, many outputs. Okay, that is 2 raised to n inputs mean, n inputs means 2 raised to n outputs. But in multiplexer it is having many inputs and only one output, and that one output is be depend upon the select lines. Okay, the expression is what of the multiplexer is 2 raised to n is to 1. That is 2 raised to n is your input, and n represents the select line, and 1 is the output. For multiplicator it will be having only 1 inputs and 2 raised to n outputs, and where n represents your select lines. Okay, see, select lines. So it is having what, n input signals, and it sometimes it is known as also as a select lines or control lines, and only one output signal. Okay, so 2 raised to n is your input, where small n represents your select lines, and 1 is the output. So this can be easily understood when we people will take one example. Okay, see, a simple one is what, 2:1 mux. A simple 2:1 mux, 2 inputs. Okay, 2 raised to 1 is to 1. Okay, where 1 is the select line. So we can consider this enable line, or we can just neglect it. Okay, See, 2 inputs, 2 raised to 1 is to 1, that is 2 raised to n is to 1. 2 is to 1 means 2 raised to 1 is to 1, where 1 is the 2 raised to 2 inputs, 1 select lines and 1 output. Okay, the boolean expression for the output is given as, say now, a simple one. It is having 2 inputs, okay, and sometimes it can be represented d0 or d1. One select lines is 0, so there is, since it is only one select lines, it will be having only 2 combinations, whether it is select line is 0 or 1. When select line is 0, what it is selected, and for select line 1, what will be the output. For select line is 0, that is s is equal to 0, d0 will be selected as a output, means whatever the value will be, d0 will be having, the same thing will be getting it as output. If d0 is equal to 0, we will be getting the output as 0. If d0 is equal to 1, we will be getting the output as 1. Okay, next, when select lines is 1, it will be selecting the d1 value as a output, means if d1 is 0, we will be getting the output as 0, and if d1 is equal to 1, we will be getting the output as 1. Okay, see here. So here is the truth table what representing. When select line is 0, d0 is selected. When the select line is 1, d1 is selected. Now the expression how we will be writing it is, see here, y is equal to what as the output, y is equal to d0 s bar. Since s is equal to 0, we will be writing it as d0 s bar plus d1 into s. Okay, see d1 and d0 and d1 and switched to the output s is equal to 0 and respectively. Thus the boolean expression for the output becomes d0 when s is equal to 0 and output is d1 when s is equal to 1. So depending upon this expression, so how we are writing the expression, y is equal to d0 s bar plus d1 into s. Okay, see depending upon this, we just draw on the logical diagram, d0 d1 and select lines. Here y0 is equal to d0 s bar plus d1 into s. Okay, in simple, what you people will be remaining for 2:1 mux is, it is having 2 inputs and 1 select line. Depending upon the select line, what it is selected, when s is equal to 0, d0 is selected, and s is equal to 1, d1 is selected. Okay, next, in the same fashion, we just go for the higher order of a mux, that is 4:1 mux. 4:1 mux. 4 means what? 2 square, that is 2 square is to 1. Okay, 2 square means it is having what? The formula for the mux is what? 2 raised to n is to 1. So what is the expression, what we can write, 4:1 can be represented as 2 square is to 1. That is, it is having 2 square as 4 inputs, and the n is what here? 2. That is, it is having 2 select lines, and obviously it is having 1 output. So this one is the block diagram of a mux, that is 4:1 mux. It is having 4 inputs, I3, I2, I1 and I0, 2 select lines, S0 and S1, and Y is the output. Okay, now S1 and S0, Y. So what it will having, depending upon the select lines, what are we selecting. So whenever S0 and S1 both are 0, 0, S1 and S0 is equal to 0, I0 is selected at the Y output. I0 means if it is having a 0 value, I will be getting it as 0, and if it is having a 1, I will be getting it as 1. Okay, next, for 0, 1, when select line is 1, S1 is 0 and S0 is 1, I will getting it as I1. When it is 1, 0, I2, and 1, 1, it is I3. See here. From the truth table, I can represent here. For 0, 0, I0 is selected. For 0, 1, I1 is selected. For 1, 0, it is I2 is selected, and 1, 1, I3 is selected. The expression for this one will be what? I0 S1 bar S0 bar plus I1 S1 bar S0 I2 S1 S0 bar plus I3 S1 S0. Okay, see the expression for this one is y is equal to S1 dash S0 dash I0, or we can represent it as S1 bar S0 bar I0 plus S1 dash S0 I1 plus S1 S0 dash I2 plus S1 S0 I3. Okay, so this one is the logical diagram what they are represented by using this expression. Next, designing of 4:1 mux using 2:1 mux. Okay, here simple design. So if you want to design by using 4:1 mux using 2:1 mux, we require 3 2:1 mux, and it can be arranged in this fashion. So if I just check this block diagram, how it will be looking like. See here. What it looks like is what? Sorry. Okay, see here. So what it is? So if I just add up with this one, what I'll be getting is 4 inputs, 2 select lines and 1 output. What I'll be getting it as a normal 4:1 mux. So first 2:1 mux will be having what? I0 and I1 as the inputs. Second 2:1 mux will be having I2 and I3 as the inputs. So it is having two outputs for I0 as well as for first mux as well as 2 mux, and those are acting as the input to the third mux. See here, S0 is being common. For these first 2 mux, S0 is common, and for third mux it is S1. Okay, see here. Now how it will be working. See here, when S0 is 0, what is happening? When S0 is 0, in this mux I0 is selected, and from in this mux I2 is selected. Okay, when S0 is 0, what is happening? From this mux I0 is selected, and from this mux I2 is selected. Okay, next one, once again S1 is 0. What is happening? When S1 is 0, the top one first will be selected. So I will be getting the I0 as the output, and S1 is 1, I will be getting it as I2 as the outputs here. So normally in a 4:1 mux, what it was happening? For when it is S1, S0 and S1 both are 0, 0, what it was happening? I0, I1, I2 and I3 was being selected common, that is 0, 0, 0. But here, see here, for 0, 0 I0 is selected, for 0, 1 it is I2 will be selected. How? From this mux, first mux I0 I am getting, from this mux I2 I am getting. When S1 was equal to once again 0, I0 I will be getting. When S1 is 1, I2 will be selected. In the same fashion, when S0 is 1, so from this mux I1 will be getting, and from this one I3 will be getting. Okay, once again when S1 is 0, what is happening? I1 I am getting as the output for 1, 0, and for 1, 1 it is I3 as the output. So this one is the design of 4:1 mux using 2:1 mux. Now next is the simple 8:1 mux. 8:1 mux means, what is the formula means? Okay, just tell me what is the formula. The formula will be what? For mux it is 2:n:1, that is 2 cube is to 1, where 2 cube is what? 8 input, and n is what? 3, that is it is having 3 select lines, and 1 is the output. A0, A1 depending upon the select line. So 0, 0, 0 what? A0 is selected. For 0, 0, 1 A1, for 0, 1, 0 A2, for 0, 1, 1 A3, for 1, 0, 0 A4, 1, 0, 1 A5, 1, 1, 0 A6, 1, 1, 1 it is A7. Okay, next the same thing we can just draw by using the what? Designing of 8:1 mux using 4:1 mux and 2:1 mux. Okay, see 4:1 mux, so we require 2 4:1 mux and 1 2:1 mux. Okay, so 4:1 mux means it is having the 4 output inputs and the next 4 inputs, 2 select lines, and for 2:1 mux it is having what? The 2 outputs of the 4:1 mux and 1 select line. So this one is the combination of the 8:1 mux using 4:1 mux and 2:1 mux. The same thing 8:1 mux can be designed by using what? Only by using the 2:1 mux. So here, see here, 2:1 mux. So we require nearly 7 2:1 mux. The 4 mux 2 4 to 1, that is D0 D1 to D1. So if I just check the block diagram, what I'll be looking is 8 inputs, 3 select lines and 1 output. So in this fashion we can just draw the 8:1 mux using 2:1 mux. Okay, thank you.